Alright, hi guys. So we're going to be finishing off some of the rules around differential calculus and differentiation. In the next video, we'll cover some of the practice functions on differentiating them with the variety of rules that we've learned in these videos. But for now, let's just have one last theory lesson for into the introduction to differential calculus. And in the next section, we'll discuss the applications of differential calculus, because at the moment, this doesn't really mean that much. Okay, so we've got two of the three trigonometric values here, sine x and cos x. And tan x we will be covering just after this, but for now it's good to start with sine and cos. So the way we differentiate sine and cos, it's pretty simple. So sine of x becomes cos of x, and cos of x becomes negative sine of x. So that's pretty easy. Now, we also need to note though, if for example we were given dy over dx of sine of 2x, we would need to use chain rule, in the sense that this would be the section we'd also need to differentiate. So as we can see in the brackets, there's 2x. Differentiating 2x gives us 2. And we just multiply it by whatever we're given here. So it would become 2 sine 2x. So remember not to just discard the 2 over here. They should just be left like this. For example, let's just take another one with cos this time. If we had dy over dx of cos 4x squared minus 2, that would become, 4x squared minus 2, let's first differentiate that. That's 8x. So that would become negative 8x, because remember cos becomes negative sine. Negative 8x cos 4x squared minus 2. So that's essentially just the basis of how you differentiate sine and cos. Pretty simple. You just take whatever is in the bracket, multiply it by the new function. So, and just before I forget, I made a slight mistake here. It's actually meant to be 2 cos x. My bad. 2 cos 2x. So yeah, anyway, you just multiply it by and you change the sine or cos. And remember that cos becomes negative sine, not just sine. So yeah, we don't want to make silly mistakes like that. Now let's think about tan x, which is, as expected, a little bit funnier than the others. Tan of x actually becomes something known as secant squared of x. And for those who don't know, which likely most of you won't, secant is basically 1 over cos x. So basically secant squared x is 1 over cos squared x. And it may look really odd to see this at the moment, but we can actually prove that tan x equals secant squared x. So first we should realize that tan of x, and note down this if you don't know already, is equal to sine of x over cos of x. This is very helpful in a variety of problems you might get on the AdMath test, but just know this. And we can actually prove it. Basically, if you think about sine is just the opposite over a hypotenuse, and we divide that by the adjacent over the hypotenuse, which is what cos is, that becomes opposite over hypotenuse times hypotenuse over adjacent, because of how you divide fractions. And these two cross out to give opposite over adjacent, which is just tangent. So going back to our main topic, I digressed a bit. Tan of x. We can use quotient rule because we've expressed it like this, and we know how to differentiate sine and cos, we can just use quotient rule. So if you don't remember, quotient rule is essentially just, the formula is just v times u differentiated minus v differentiated times u over v squared. So in this case, our v is the denominator. So v is cos x, and our u is sine x. And then differential of v is negative sine x, and the differential of u is cos x. All right, now we're ready to substitute all our values into the quotient rule, which we see over here. So, that's a bad line, sorry. Let me just correct that. So we multiply v by the differential of u. So v is cos x, and u differentiated is cos x as well. So that's cos squared x. And then we subtract that from the differential of v times u, which is let's just put this in brackets because we have a negative sign here, so in case, which is negative sine x times sine x. And that's divided by, so v squared. So v is cos of x, and cos of x squared is cos squared x. So we have over here cos squared x plus sine squared x over cos squared x. And another thing that you might not have learned yet, but I'll cover it more in the trigonometric identity section of the video, is that sine squared x plus cos squared x is actually equal to 1, which means that this can be crossed out and replaced with 1. So we have 1 over cos squared x, which is equal to secant squared x. And don't worry if you don't really understand what secant is at the moment. I'll explain it later in the trigonometry section, or the trigonometric identity section rather. So yeah, that's tan x. Now what we'll move to is e to the power of x and ln x. Okay, so I've just written dy over dx of a times e to the power of bx, and a and b are both just random constants. I'm essentially just showing the way you'd express the differential of e to the power of x. Well, let's first cover what e to the power of x is, because I don't think I've gone over this well enough, but essentially e to the power of x can be related to ln of x. And in the logarithms thing, we talked about how ln is the natural logarithm and that it has base e. So what exactly is e? E is also known as Euler's number, and it's basically like 2.718 approximately. But it's just a very special number. That it's a bit like how like pi is quite a random number, but it's like pretty special. It's a bit like that. So I don't really have a good explanation as to why e exists, and I don't think you need it for the add math syllabus, so I won't really go into that. So essentially, you will still need to know how to differentiate e in the add math syllabus. So let's say that a and b are in their respective locations, and you made it a times e to the power of bx, and you want to differentiate this. I don't really care about what a and b are at the moment. I just want to like give the general formula or way of expressing it. And it's essentially going to be written as ab times e to the power of bx. So this, let's just say a is 3 and b is 2. So if you have 3e to the power of 2x, then this would become 3 times 2 times e to the power of 2x, which is just 6e to the power of 2x. So you bring down whatever's in the power section of e and multiply it by 3. So you might be wondering, well, this looks a bit different. This doesn't really look like it doesn't really look like the power rule, because isn't this supposed to decrease by 1? Well, it's because it's being raised to the power of e, not being raised to the power of x. So it's a bit different that way. So essentially, another way of expressing this is if you had e to the power of x squared, well, you'd multiply whatever this differentiates to down here and leave this as it is. So in this case, x squared is differentiated to form 2x. So this would become 2x times e to the power of x squared. You don't change the power. You just differentiate the power and multiply it by whatever e is. So we could say also what happens if we have e to the power of 4x squared minus 2. Well, 4x squared minus 2 differentiates to 8x. So we'd have 8x e to the power of 4x squared minus 2. And we can also differentiate ln. So while we have e to the power of x, which is fairly straightforward, ln is also pretty straightforward. So let's say we had dy over dx of ln of 3x squared minus 2x plus 1. Well, essentially what we need to do is set it in a way where we have the differential of ln in the differential whatever's in the brackets of ln in the numerator and the actual function itself in the denominator. So what I mean by this is, let's represent this as ln u. And essentially the way you would differentiate it, let me just write the notation there, dy over dx is equal to the differential of u divided by u itself. So in this case, we can say that u is equal to 3x squared minus 2x plus 1. And u, the differential of u, is just 6x minus 2. So we can plug it into our equation and we get 6x minus 2 divided by 3x squared minus 2x plus 1. And yes, the ln just goes away, just evaporates. And that would be how you get from here to here in terms of differentiating it. So ln itself is also pretty simple. And let's just say you had 3 ln 3x squared minus 2x plus 1. You would multiply this by 3 to give 18x, let me write that again, 18x minus 6 divided by 3x squared minus 2x plus 1. And that's your final answer. So there you have it. That's all for this video. Just wanted to clear up some of the last things that we need to be able to differentiate in GCSE level, AdMaths level. And in the next video, we'll go over some practice like functions to differentiate so that we have a good understanding of it. And then after that, we'll start on the actual applications and how we're going to use differential calculus. So thanks so much for watching and see you in the next video.